Hello and welcome to the first lesson of our next unit for functions, where today we are starting our unit on exponential functions. But before we get into the functions themselves, we are looking at what exponents are and exponent laws. So our learning goal today is to be able to use laws of exponents to determine different expressions using exponents, but specifically with rational exponents. So any exponent that can be expressed as a fraction. So as shown here, for example, x to the power of m over n. So our exponent here is m over n, which is a fraction. So to begin, we're going to consider an example. Let's say a person A has a piece of information and they want to share it with other people. For example, this could be an information that needs to be shared within a company or a group of friends, or for example, you can think of this as how gossip spreads. So, person A has a piece of information, they tell it to two other people, person B and person C. Then each of those two people tell two other people. So B tells D and E, C tells F and G, and then so on and so forth. D tells two other people, E tells two other people, F tells two other people, and G tells two other people. And as this continues, we can see that this is growing rapidly. And actually, it is growing exponentially. And so this helps, for example, when a piece of information needs to be shared, using this strategy, you can share it to many people really quickly instead of each person telling one other person, which would be more of a linear spread. So we are asked here, how many people end up hearing about the news? And we're, for example, just considering 5 rounds of sharing here. So in the first round, so right now only the first person knows, and that's person A. So here we write this as a power of 2, 2 to the power of 0. Then in the next round of information shared, so this is now the first round, which is this first row we saw here, A has now told person B and C. So now two people know information here. And we're only looking at the rows. We're not looking at the total. We're just looking at now for example, this is row 0, this is row 1, this is row 2, row 3, and row 4. And so the number of the row is actually going to be the power of 2 that we see here. So here we would have 2 to the power of 1. Now in the second round, which is row 2, we clearly see the 4 here and we have D, E, F, and G. So now 4 new people know about this. And perhaps maybe this should be number of new people. Not number of total people who know the information, but number of new people who now know about this information. Now the next round, or row 3, as we see here, this is 8, which is 8, which was that 4 times 2. And as you see here, the power of 2 is growing by 1, and these are growing by times 2. And so following this pattern, even though row 5 is not shown to us, we would expect there to be 32 people there. And on the power of 2 column, as we fill this would be 2 to the power of 4, 2 to the power of 5. So to know the number of people, how many people end up hearing about the news, you would just have to total all of these up, all of the powers of 2 or all of their results here. You can add them up to know how many people now know. And this is pretty much what exponents are. So you are multiplying by a certain number each time. So let's get to the definition of an exponent. So an exponent is pretty much repeated multiplication, as we were just seeing here. We were multiplying by 2 repeatedly. So we were multiplying by 2 there because our base was 2. So the number being multiplied repeatedly was 2 here. And our exponent, which was changing each time, is telling you how many times the multiplication is happening. So for example, when we had 2 to the power of 3, this is 2 times 2 times 2, 3 times, and this would give us 8. So when you have a base a to the power of n, that means a is being multiplied by itself n times. So let's look at some examples now. So here we have 2 to the power of 3 times 2 to the power of 2. So I'm going to write this in two different ways for you to see. So this could be 2 times 2 times 2, and this one could be 2 times 2. And now if I count in total how many 2's there are here, this would be 2 to the power of 5. And you can actually check. So this is the other way. This would be 8, and this would be 4. And 8 times 4 is 32. And you can precisely check that 2 to the power of 5 is 32. Now, 2 to the power of 6, again, if I write it out. Okay, there we go. And then divided by 2 times 2. And perhaps let me write this as a fraction, which might be a little bit easier to see. Because remember, division is just a fraction. So if I have this form, then really I'm just simplifying out those two 2's, and I am left with 2 times 2 times 2 times 2, or in other words, 2 to the power of 4. And again, you can double check. This is 64. 2 times 2 is 4, and 64 divided by 4 would give us 16, which is also precisely 2 to the power of 4. So now I want you to think, just looking at these two examples, and you can even come up with your own examples, try a few on your own, but what is the rule for multiplying powers with the same base? And also, what is the rule for dividing powers with the same base? So here we saw we had 3 2's and another 2 2's, and when we multiplied them in total, we had 5 2's. So a rule for multiplying is that with the same base. So when you're multiplying powers with the same base, the base stays the same, but the exponents or the powers are added together. And that's what we saw here, right? 3 plus 2 gave us 5. Now, for dividing powers with the same base, again, the base stays the same, but here the powers are actually subtracted from one another. And I do have the definitions for these in the next page, so I'm not going to write the actual formula for it here. But with division, we know that you can't just switch the order in division, so it has to be in that same order. So here we saw 6 minus 2 gave us 4. And as we can see, the bases all stayed the same. It's just that powers were now subtracted from each other. And we showed that with the fraction form as well. So this actually gives us two exponent laws here, or exponent rules, starting with the product rule. So when multiplying powers with the same base, you add the powers. So remember, the dot is just multiplication, so this is also can be written that way. The reason we just don't do that is because sometimes your variable can be x, so the base could be x, and then it's a little bit confusing to write x times x. I usually write my variable x with cursive to distinguish it from the multiplication, but still you can see it can cause some confusion. So often you will see the dot used as the symbol for multiplication. So here we have the power m and the power n. So our product, we have the same base, a, and now the two powers or exponents are added together. So m plus n. And here's another example with the base of 2, 2 to the power of 3 times 2 to the power of 5. We keep the base, but now our exponent is 3 plus 5, which gives us 8. And you can actually evaluate this for yourself. 2 to the power of 3 is 8, and 2 to the power of 5 is 32, and 8 times 32 will give you 256. So now I suggest you take a moment and try these on your own. You are just simplifying here. And two terms I'm going to actually bring your attention to here are simplify versus evaluate. So whenever you are given simplify in the instructions, especially with exponent laws, you are just asked to use the exponent rules to write it as the simplified form. So for example, here, the simplified form would be 2 to the power of 8. However, if you're asked to evaluate, that means we want a final answer. So you would even have to solve for the exponent, which would be 256 here. So actually, maybe let me write these beside this. So if you were asked to simplify, your answer would be 2 to the power of 8. But if you're asked to evaluate, your answer should be 256. So keep in mind this is simplify. I'll give you a minute, try these on your own, and then I'll show you the answers. So you should have got the following, and I'll just briefly explain each of them. So this one is pretty simple. 3 plus 12 is 15. We keep the same base. Now here's where you might have had a little bit of confusion with that a on its own. Remember, a or any variable with no power actually has a hidden power of 1. It's a to the power of 1 is a times itself, or a by itself. So a to the power of 1, we have 7 plus 1, which gives us 8. Now, this one was meant to trick you a little to see if you get confused by that negative, but it still follows the same rule. You are really doing 4 plus 3 plus negative 5, which gives you 2. So then you would have pi to the power of 2. And also, you don't necessarily need to have like a rational base. Here we clearly see that pi could be our base, and it still works. You would just have pi times pi here because it's power of 2. Now the quotient rule is for division. So when dividing powers with the same base, so division is shown here as the fraction form, you subtract the powers. So here, a to the power of m divided by a to the power of n will give you a to the power of m minus n. And remember, we keep that order. So this would have also been, could have been written as a to the power of m divided by a to the power of n. So then m minus n. And here again, another example with a base of 2. 2 to the power of 7 divided by 2 to the power of 3 is 2 to the power of 7 minus 3, which is 4. And our final answer is 16. Now again, here we have simplify. So take a moment and try these on your own. So these are the values you should have gotten. So here, 3 to the power of 12 minus 3 to the power, or divided by 3 to the power of 8 will give us 12 minus 8, which is 4. Again, keep the same base. Here we have that hidden exponent of 1. So we would have 9 minus 1, which gives us 8. And again, keep the base b. And this one actually had 2 steps. This is times and then divide. And remember, when you have multiplication and division, when we are following the order of operations, BEDMAS or BEMDAS, whichever one you are familiar with, the M and D are actually interchangeable. So it doesn't matter which order you do them in, but generally you do them in the order of left to right. So here, I would solve this first, or evaluate or simplify this first, which would give me pi to the power of 7, because 5 plus 2. And then this is divided by pi to the power of 3, which gives me pi to the power of 4. Now, how can we solve something like 7 to the power of 2 in a bracket, and then this to the power of 4? This is also still an exponent, but now consider this here. Your base is 7 to the power of 2, and the exponent or power is 4. So really, you are multiplying 7 to the power of 2 by itself 4 times. And that's what is written here. We're considering it as repeated multiplication. So 7 to the power of 2 times 7 to the power of 2 times 7 to the power of 2 times 7 to the power of 2, 4 times. This is 4 times. And now we're just applying product rule, right? Because these are the same base multiplied. And now 2 plus 2 plus 2 plus 2 is 8. But really, this was also 2 times 4, which was 2 times 4. And this actually brings us to our next exponent rule, which is the power rule. So when a power is raised to another power, you keep the base, but then you multiply the two powers. So here, a to the power of m, this could be considered as a whole base, and this is to the power of n. But then when you are repeating m n times, really you're doing m times n, right? So that's how you get that power there. So 2 to the power of 3 here, and this as a whole raised to the power of 4. So keep in mind, we need the bracket to show that. This is 2 to the power of 3 times 4, or 12. And if you evaluate, this is 4,096. So we're going to try a couple examples first together. So here we have m to the power of 4 times m to the power of 10 divided by m to the power of 5. So this is actually meant to trick you a bit. This is not a power rule. This is simply just a product rule because it's m to the power of 4 times m to the power of 10, right? So m to the power of 4 times m to the power of 10 will give us m to the power of 14. This is just product rule. Now, m to the power of 14 divided by m to the power of 5 will give us m to the power of 9. So this whole thing will be m to the power of 9. Now, in this, let me just write my 9 better. Okay, there we go. Now, in this next one, we do have now power rule because we have the bracket and now there's an exponent outside of the bracket. So I'm going to do this in one step here. Or not one step, but all together. I'm not going to separate it the way I did with the example above. Okay, so 4 to the power of 8 to the power of 2 first will give us 8 times 2, which is 16. Now, in the denominator, I will have 3 times 5, so 15. Now, I will simplify the numerator first. So 4 times 4 to the power of 16 is just 4 to the power of 17. And now here, 4 to the power of 15 stays the same. Now here we have 4 to the power of 17 minus 15, which is just 4 to the power of 2. Now, keep in mind here, you are asked to evaluate. So we do solve 4 to the power of 2, which is just 4 times 4, and it gives us 16. And we would be done there. And you can try just inputting this into a calculator as well, and you will see that you should get 16. Now, keep in mind with an exercise caution when you are inputting powers into calculators, the order really matters. So you have to pay attention that you have the same setup. So depending on your calculator, if you switch the order of any of these or like something is going wrong, you may get a different answer. So that's why it is important also to learn exponent rules so you can split it up and evaluate it by parts to make sure all the rules are being followed as required. Now, so far, we did work mostly with positive exponents, except for that one example with pi where you had a negative exponent, but we didn't really go too much into it. But you could have negative exponents as well. So specifically when we are looking at integer exponents, so remember integers are whole numbers. They can be negative or positive as well as 0. Then we're going to consider the 3 cases here with positive integers when the exponent is 0 and also negative integers. So with the positive integers, that's what we've been seeing so far. It's just repeated multiplication, and a to the power of n will be a times itself n times. Now, a to the power of 0 is one of our special cases here. So a to the power of 0, or any base to the power of 0, is actually equal to 1. With the exception of when a is equal to 0, we don't that one is actually an undefined case. And after I show you negative integers, I'll go back into why that one is an undefined case. So with negative integers, you actually take the reciprocal of the positive exponent. So when you have a to the power of negative n, this is just 1 over a to the power of n. And again, a cannot be 0 because if it was 0, then 0 times itself n times is just 0. So this would be an indeterminate case, so we cannot have 0 in the denominator. Now, to show you briefly why, let me go over here. So consider you have 1 divided by 4 to the power of 3. Now, based on what we do know just by operations, this is 1 over 4 to the power of 3. But we can also write 1 as 4 to the power of 0, as we just saw. And then divided by 4 to the power of 3. Now, this can be just our quotient rule, which told us 4 to the power of 0 minus 3, which is 4 to the power of negative 3. But then 4 to the power of negative 3 is 1 over 4 to the power of 3. And that's exactly what we see here. Now, I can also use this to show you why a to the power of 0 is equal to 1. So consider 4 to the power of 3 divided by 4 to the power of 3. So we know that this is 4 to the power of 3 over 4 to the power of 3. This is just 1, right? Because anything divided by itself is 1. But using our quotient rule, this is also equal to 3 minus 3, which is 4 to the power of 0. So that 4 to the power of 0 is equal to 1. And that's the justification behind that. And so you can see why if you have a base of 0, then you would have a denominator of 0 in the division, and we can't actually have that. So that's why a cannot be equal to 0 in the case where the exponent is 0 or a negative. But you can have a base of 0 with a positive exponent. So if you have 0 to the power of 5, this is just 0 times 0 times 0 times 0 times 0, which is just 0. So 0 to the power of any positive integer is just going to be 0. So here's exactly what I just shown you up there with another example. So 8 to the power of 3 divided by 8 to the power of 3 is equal to 1. We just know it as a rational number, but using the quotient rule, we have 3 minus 3, and this is 0, so 8 to the power of 0 is 1. And you can change the base to any base, and the rule will still hold. So now we're going to evaluate these next two examples. So first, negative 4 to the power of negative 3. So I'm going to write this as first the positive exponent. There we go. And now I'm just going to first, just to show you, expand this. So this is negative 4 times itself 3 times. So we know that 4 to the power of 3 is 64. But now we have the negatives, and there's actually 3 negatives, which means our final answer will be negative 64, because 2 of the negatives will multiply to become a positive, but then you have another negative left. So negative 64. And that would be the final answer there for evaluation. You don't need to go into decimals. Fraction form is okay. Now, with this next one, let me rewrite it. So with powers, powers actually have the distributive property, which means that I can write this as 3 to the power of negative 2 and 5 to the power of negative 2. Now, this will be, and maybe I'll separate here, divided by 1 over. So 3 to the power of negative 2 is just 1 over 3 to the power of 2, the reciprocal, and the same thing. This is also now, or sorry, this should be, because I use divide, then it's just, there we go. And this is now taking the reciprocal of this. We have 1 to the power of to the power of 2. But this is a division, so then really we keep the first term, so 1 to the power of, or sorry, 1 over 9. Now multiply by the reciprocal of this, so 25 over 1, and this is 25 over 9. I want to show you maybe another way you can consider this. You can also consider this 3 to the power of 5 to the power of 2, and this itself is to the power of 1. Because remember, this is just power rule, right? 2 times -1 will give you -2. Now, first I'm going to evaluate this part, which is 3 times 5 times 3. Sorry, 3 over 5 times 3 over 5. And then inside this bracket, I just have 9 over 25 and then -1. And remember, the negative exponent tells us reciprocal. So the reciprocal of this would be 25 over 9. So the same answer. And really, I could try this with other methods as well. You can first do the reciprocal and then take the power of 2, and you'll see that any way that you try, you should get 25 over 9 as your final answer. Now, our next example, we want to simplify and find a value for n that will make the statement true. So first we start by simplifying. So n to the power of 2 times to the power of 5 is going to be n to the power of 2 times 5. 5. Now here, this will be n to the power of 10 divided by n to the power of 5. And then this is just n to the power of 5 because we're subtracting. So now this is, when you get to this part, you have two ways. You can either try to use trial and error based on the numbers you know, based on the values you know, but there is actually an operation for this. So if you remember roots or radicals, they are the opposite operation of exponents. So for example, when we have 5 to the power of 2 is 25, if we take the square root of 25, which is actually a radical with a hidden 2 there, this is 5, which tells us 5 to the power of 2 gives you 25. Now, since we saw the examples with 2, 2 to the power of 3 was 8. Now, if I take the cube root of 8, so now there's a 3 there, what I'm asking is, what number to the power 3 will give me 8? So what number multiplied by itself 3 times will give me 8? And you will find that this is 2. So on your calculators, you should typically have one button. I know mine looks like this. Maybe let me just change the color to this one. Of this one, and it looks like this. So when you input this, so when I input this on mine, it first asks me for the value here. So in this example, I want to take the 5th root of 243. So I will input 5 first, and then 243. And I don't know if it'll show. There we go. Kind of does show my calculator. And now, if I evaluate this, I see that I get 3. So what that tells me is 3 to the power 5 will give you 243. So then n is equal to 3. And you can always double check. Now 3 to the power of 5 here, I'm going to evaluate. 3 to the power of 5 gives me 243 as required. So whenever you have to solve for the base, you can always use this tool here on your calculator. Now, in this next one, you have, again, different options. So I'm going to start by evaluating the bracket. So m to the power 7 divided by m to the power 6. This is just going to be m to the power of 1 squared. So this one's actually simple because 1 times 2 is just 2. So this is m squared is 196. So this is just what we're used to, square root of 196. And your calculator should have just an automatic button for square root where you don't need to put the index here because it's automatically known as 2. And if you evaluate this, you get 14. So m is equal to 14. And I'll leave this one as an example for you to try on your own, but show that this expression here, if you simplify it, will evaluate to 390,625. So now that we saw the positive integer, negative integer exponents, now we're going into rational exponents. So rational exponents are exponents that can be written as a fraction, m to the power of n. So m and n are integers, and n is not equal to 0 because this is just a property of fractions where you cannot have a denominator of 0. So when you have a to the power of m over n, this is also a to the power of m, and we have the radical with the index n. Or really, a to the power of 1 over n is also the radical with index n. For example, over here, a to the power of 2 over 3. So the 2 is the power 8 squared, but the 1 over 3, or the denominator of 3 here, actually tells us to take the cube root. So here we have the radical with the index 3. So I start, and you can do this different ways. So you can start by doing 8 squared and then take the cube root of 64, or you can take the cube root of 8, which is 2, and then square that and you get 4. Both of these will give you 4. And so that's how we evaluate rational exponents. So let's see a couple examples there. So here, 65 to the power of 1 over 3. So this is the cube root of 65. And I've shown you here now the visual of how you input this on your calculator. So your calculator should have like a button like this, or this one itself, the n could be a box itself, the way it's shown on mine. So when you first press this, you press 3, which is the index, so the root that you want to find. And then you press 65 to input what goes under the radical. And here, when we press equal, we get 4.0207. And you can round this to just 4.0207. You don't need the rest. So here, we are now asked to evaluate 3,125 to the power of 0.2. But 0.2 is really just 1 over 5. So this is just the fifth root of 3,125. So again, if you input this into your calculator, you first press this button, then you press 5 because the index here is 5. You want the fifth root, and then you press 3,125 and you should get 5. And in other words, and I'll write it for both of these, 5 to the power of 5 is 3,125. And similarly above here, if we have 4.0207 to the power of 3, this is approximately 65. Now, in this next example, negative 27, now we're just combining all the things we've learned so far, negative 27 to the power of negative 2 over 3. So first, I broke apart the radical exponent, so 1 over 3, and then negative 2 is the outer power. So I'm first evaluating this inner part. So negative 27 to the power of 1 over 3 is just the cubic root of negative 27. And again, if you put this into your calculator, you don't have to worry about the negative. It will input or evaluate the negative for you. But the reasoning for this is negative 3 to the power 3 gives you negative 27, whereas 3 to the power 3 just gives you 27. So to have that negative there, you do need the negative in your base as well. And so um, the inner bracket will give me negative 3. And then I have that negative 2 as my outer exponent. And so this is just 1 over negative 3 to the power 2. Remember, we take the reciprocal of negative exponents, which is 1 over 9. And that was the end of our lesson on exponent rule. So you do have some practice problems here as well as a practice set on Google Classroom. And as always, don't hesitate to reach out if you have any questions, and I will see you all next class.